Okay, so this is the MATLAB assignment number 2. It's due on Thursday at midnight. So you have questions. You have a chance to ask me questions tomorrow and on Thursday. Okay, so this is a heat equation problem, but it's based on our homework. Our homework as assigned homework is exercise number 3. Okay, exercise number 3. It's a different boundary condition. The boundary condition is the two ends are insulated. Yeah. So two ends are insulated. The initial temperature, so the two ends, so I provided a solution. So I'm going to show you the solution I provided to you. I already provided a solution for, let's see, is here solution for heat equation, wave equation. And this is the solution provided by the publisher. So it's not very detailed. And then today I'm going to assign another homework question is the wave equation. After I finish wave equation, it's going to be one problem only, problem 11. So this is problem, this is the two problems. Okay, two problems, one for heat equation, one for wave equation. I'm going to choose one question for the quiz number 4 question. Okay, quiz number 4 is next Monday. Okay, quiz number 4 is next Monday. Because the solution provided by the publisher is not very detailed, so I did provide detailed my handwritten solution. For example, for heat equation, so this is the handwritten solution. Hold on one moment. So this is my handwritten solution, shows all the steps. Okay, shows all the steps. And then we have a final solution I put in this box here. The same thing for the wave equation. And then the MATLAB problem is based on the this heat problem with insulated ends. However, the FX is initial condition. I provide initial condition as you can see here. This is my FX function. Okay, this is my FX. Okay, my FX, and then you need to use symbolic calculation to evaluate the two integrals. Okay, so I show you how to use symbolic calculation. And then I think this homework question is a little bit more, I guess, more of thinking involved as compared to the first one. Because first one basically just use my code and change the parameter. You get it. But this one is a little different heat problem. So it requires a little explanation in the end. So I did have a detailed requirements. Okay. So with that being said, I'm gonna just write down the on the board. Stop share. Let me see on the board. Board view. So homework number 4 is 13.3 is the heat equation problem number 3, and 13.4 wave equation problem number 11. Okay, and then quiz number 4 is going to be Monday, next Monday. Okay, next Monday, and midterm exam. Let's say Wednesday. Okay, Wednesday. But however, I'm going to finish the content this week. Okay, I'll give you a few days, like a time to prepare for the midterm. It's next Wednesday. Okay, it's next Wednesday. Like here, okay, and MATLAB number 2 is based on this problem. Okay, is due Thursday midnight. Okay, it's due Thursday. This is next Monday. Okay, next Monday. Next Wednesday. And this Thursday midnight. Okay, 11:59 p.m. online. Okay, so that's all the assignment. Is that clear? Yeah. Okay. Okay, so
Now we're gonna have a like a review sheet for the midterm.
yes, I will have a review sheet for midterm. So yeah, I will the midterm. I will provide it after class today.
Okay.
Okay, our review sheet.
You're gonna just post it.
Yeah, I'll post it after class today. And we're gonna just have today's topic is wave equation. Try to do a lot of simulations. If not, then I'll do simulation tomorrow. And then we have Laplace equation.
Okay.
And I'm gonna jump to the Laplace equation in the polar coordinates rather than the rectangular coordinates. So that's the next chapter. Okay, so that's that.
And then tomorrow we're just doing wave equation today.
Wave equation today and Laplace equation tomorrow and Thursday for including the simulation. I'll go run simulation for each problem. Okay, I'll run MATLAB simulation for each problem. Okay, so let's start with wave equation. With the wave equation, 13.3. We have wave equation for vibrating string. Wave equation of vibrating string. Okay. So let's consider. Let's look at this is a physical problem. Consider a small transverse vibration of an elastic string so it's like this. I have okay, so I have X and Y. Consider a string is like this. The string is placed along the x-axis. Okay, suppose the string, I'm going to use different color. Suppose the problem is the string is fastened at the end, at the two ends. The string has a length of L, okay, from 0 to L. Okay, from 0 to L. This is the x-axis. Okay, the string is fastened on the two ends. Suppose the initial condition is something like, initially the string is like, okay, it's like being stretched, for example, like that. Okay, and then and then it's going to vibrate. The two ends are fastened. Okay, the two ends are fixed. Okay, and this is your vertical displacement. This is your vertical displacement. Okay, so okay, that's the problem. One is the string is placed along the x-axis stretched to length L. Okay, and fastened at ends x equal to 0 and x equal to L. Okay, x equal to 0, x equal to L is fastened. Okay, so and this height is we call u. Okay, u is the height. X is their the length. Okay, their u is the height. Okay, the height of their for each position of the string. There's a vertical height. Okay, vertical height, or you can say vertical displacement from the zero height. Okay, from the zero height. Okay, second is this. The string is then distorted. For example, you can physically just use your hand to pick up the string. So it's distorted, but you picking it up because it's perfectly elastic. So you can stretch it. You can stretch it by just picking up with your hand at different positions, or you pick up with a whatever a rod or something, so that you can you have multiple point of contact to pick it up. Okay, and at t equals 0, and at t equal to 0, it is released. It is released and allowed to vibrate. Okay, and allowed to vibrate. So the problem is this. The problem we're trying to solve is to determine the vibration of the string. What do I mean vibration of string? Is I want to determine for every position of the string, what is there for every location along the string, what is their vertical displacement at any time? Okay, at any time. So that is what do I mean the vibration? Is we call deflection. Deflection, or which is their vertical displacement. Vertical displacement is just the height. Okay, the height, which is u as a function of x, and t at any point x, which is x is between which is between 0 and L, and at any time t bigger than 0. Okay. So to determine the vibration of spring, that is the deflection or vertical displacement, u as a function of x, which is position, as a function of t. Okay, x is between 0 and L. Okay, t is bigger than 0. Okay. So this is the physical description of the problem. So let's reduce this into mathematics. So what is mathematics? So in this case, for this problem, u is displacement. Okay, u is the vertical displacement, or the height. Okay, the height of the height. Okay, so I'm not going to derive the wave equation. The book derived the wave equation. So this boundary value problem is this. Our boundary value problem is, our heat equation is a squared partial square u partial x squared equals to partial square u partial t squared. Okay, so that's the wave equation. So I'm not going to derive it. So x is from 0 to L, t is bigger than 0. Okay, let's look at the boundary condition. What is boundary condition? The left end is fixed at 0 height. right end is also fixed at zero height. So that's why U 0, T is 0. So that means what? That's left end is fixed at zero height. Okay. From the x-axis, the height, and then U, L, T equal to 0. So this means the right end is also fixed at the zero height. Okay, from the axis, from the x-axis. So this is two initial conditions. Both ends are fixed at zero height. And then initial condition is what? Initially, let's say I'm going to just make it general to solve it. The general problem is initial position. For example, this is initial position follows a function fx. Okay, so u x 0 initially when t equals to 0 is a function of fx. Okay, is a function of fx. Okay, notice that this boundary equation, x is second order. So we have two boundary conditions. T is also second order. So we actually requires two initial conditions. One is called initial position. This is initial position. Another one is initial velocity. Means if you pick it up, maybe there's initial like a velocity associated to it. For example, maybe every point has they're still moving at time equal to 0. They have a velocity. Every point, maybe there's certain velocity associated to it. Okay, suppose they're all moving up. So what is velocity? When you have a u is displacement. Velocity is what? Derivative in terms of time. So it's partial u, partial t. Okay, it's partial u, partial t. You know, u is displacement. This is the change of displacement in terms of time. The rate of displacement change in terms of time is velocity. Okay. Initially, when t equal to 0, this is initial velocity. Initial velocity is gx. Okay, follows the function of gx. So that is my mathematical description of this physical problem. So there is two ends. This boundary condition, two ends are fixed at zero height at all time. At all time. Okay. And initial conditions, this is your fx, is initial position of the string. And this is the initial velocity. So every point, maybe they're still moving at time equal to 0. Okay. So there's an initial velocity. So that is the entire boundary value problem. Okay. Two boundary conditions because this is second order in terms of x. Two initial conditions because this is also second order in terms of t. Okay. So let's look at let's solve this problem. Okay, I'm going to erase this. Okay. Oh, I don't use this. Okay, I'm going to erase the whole thing. Okay. So we start with what? We start with our gravity equation. What should we do?
Rewrite it.
What?
Rewrite it.
What do you mean rewrite it? We have to solve it.
Right.
We have to solve it using separation of variables, right? This is actually our homework. This is a homework question. This is a homework. I assigned this as a homework question. I just didn't pick it for as the quiz, but it's one of the homework questions. Remember? It's one of the you should remember it's one of the homework questions. Okay.
Yeah, the one that we just got today, right? You just assigned to it.
No. It's a homework question. Let's just show you your screen.
Yeah, you didn't tell me.
It's not assigned today. I assigned it's the last one. It's the last homework question. Homework 3. Okay. Let me just open this for you. Okay.
You're talking about when there are two.
This one here, number 11.
Yes.
Number 11. Okay. I just didn't pick this for the as the quiz for yesterday's quiz. I picked another question, but this is the okay. This is one of homework questions. Okay, let's do it. Well, let's do the separation variables. So start with the boundary condition. Start with the governing equation. Let's do separation of variable. So separation of variable. Separation of variables. We assume is a product solution, right? U as a function of xt can be considered as a function of x, and a function of t. Okay, so capital X is a function of x, capital T is a function of t. Okay, so that we have, of course, we have this. We have partial square u, partial x squared is going to be x prime t, and partial square u, partial t squared is x t prime. So we plug this into our equation. Is a squared x prime t equals to x t prime. Okay, and then we separate them. I'm gonna a squared can be on the x side or t side. It doesn't matter. So I'm gonna put on the t side. Okay, x prime over x equal to t prime over a squared t. Okay, a squared t. So what should we do next? They have to equal to lambda. Okay, lambda is a constant. Okay, now we have two ODEs now. Okay, ODE 1 and ODE 2. So now we have ODE 1 is going to be x prime x equals to lambda. Okay. And ODE 2. The ODE 1 is basically just x prime minus lambda x equal to 0, right? And x and t prime a squared t equal to lambda, which is just t prime minus a squared lambda t equal to 0. Okay, so I'm gonna start with ODE 1 because ODE 1 is a little simpler, but ODE 1 and ODE 2 essentially is the same, right? It's the same. It's just this one has a little coefficient. Okay, let's start with ODE 1. So start with ODE 1. Okay, start with ODE 1. So we have x prime minus lambda x equal to 0. So what should we do? What should we do? Okay, so we need to break down into 3 cases because depending on the sign of lambda, we could use the this second one or the third one. Okay, so that's why we have case 1. Case 1 is when lambda is 0. What's the solution when lambda is 0 here? So we have x prime equal to 0. Then we have x as a function of x in this case should be equal to I call c1 plus c2x. Okay, c2x. Okay. I need a little more space. Yeah. Okay, I'm gonna okay, I can build a little more space. Okay. Okay, so now let's look at this boundary condition. These are two boundary conditions, okay? This is our, I'll just write down a little to the left. So I have a little more space, okay? Boundary condition is condition. Okay, a little more space. Okay, so we're gonna start with their boundary condition. Okay, let's start with the boundary condition. Boundary condition is this. Boundary condition is we have U0T. U0T is actually X0TT. Okay, X0TT. So because TT cannot be zero, so that's why X0 has to be zero. Okay, because if TT is zero, then it just then the U is the zero every time. U is zero at all times.
Right.
Okay, so that's why this equal to zero. So this has to make sure this indicates X0 is zero. Okay, same thing for this one. LT is XLTT equal to zero. Okay, equal to zero. So this actually means XL has to be zero. Okay, so let's plug this two boundary conditions into here. So now let's see, X0 equal to zero. That means here is C1 plus C2 zero. Okay, so C1 plus C2 zero. Zero equal to zero. So that means C1 is zero. Okay, XL equal to zero. That means C1 is already zero. Then C2L is zero. So that means C2 is also zero. So this is what we get trivial solution. Okay, this we call trivial solution. Trivial solution. Okay, so we eliminate this case number one. Okay, case number one, only without trivial solution. Okay, so let's look at the case number two. Case number two, let's assume case number two is when lambda is bigger than zero. Okay, when lambda is positive. So that's why we assume lambda. We can assume lambda equal to alpha squared, where alpha is bigger than zero, so that our solution, our equation becomes, or this ODE1 becomes x prime minus alpha squared x equal to zero. Okay, based on that form, based on the table, which one should we use? Which one?
Based on that table, you should use the third.
The third one. Okay, should we use exponential form or hyperbolic sine and cosine form?
Hyperbolic.
Okay, let's use hyperbolic sine and cosine form. Okay, so that we have x equal to, in this case, is going to be, I already use C1, C2. So I use C3 cosine H alpha x plus C4 sine H alpha x. Okay, so with same thing, we're gonna plug into these two boundary conditions. So this is my new boundary condition. Okay, there's two boundary conditions. Okay, apply boundary condition. Boundary condition, we can say x0 is going to be C3 cosine H0 plus C4 sine H0. Remember, cosine H0 is what? Do you still remember that? Cosine H0. Let's look at it. Let's look at it again.
Going to be
Let's look at the curve. Cosine H is like what, right? Like this. This is cosine HX. and this is 1. Okay, and sine hx is okay. Cosine hx is this. Sine hx is like this is sine hx. Okay, so this one is sine hx. Okay, this is x. So you can see that cosine h0 is 1. Okay, so this is 1. This is 1. This is 0. So this equal to 0. That means C. Okay, so this is C3. Okay, and then C3 is 0. Okay, because it's 0. Okay, now C3 is 0. Okay, let's look at XL. C3 is 0, so we don't even need like this part. So it's going to be C4 sine H alpha L. Okay, now we do the same thing. Alpha is positive, L is positive. Okay, this is bigger than 0. Then this entire thing is going to be bigger positive values, not going to be 0. Okay, so because this is bigger than 0, so this entire thing is bigger than 0. So if this has to be equal to 0, that means C4 has to be 0 because this is the positive value. Sine H is positive value. Sine H alpha N. The alpha N has to be somewhere in the positive side. Okay, so that's why we have forced C4 to be 0. Then what happened? This is another trivial solution, right? Trivial solution. We've done this so many times. So we've done this in the heat equation. The same thing applied to this. Now we eliminate this case number 2 because it results trivial solution. So now let's look at case number 3. Okay. Case number 3. Lambda is like this. Okay, then we assume lambda equals to minus alpha squared. Well, alpha is bigger than 0. Okay, so that's what we do. And then this equation becomes x prime prime minus alpha minus becomes plus alpha squared x equal to 0. Okay, so that now we're going to use their second one. Okay, so the solution for this is x as a function of x equals to, I already use C3, C4. I'm going to use C5 cosine alpha x plus C6 sine alpha x. So let's plug into the boundary condition. X0 equals to C5 cosine 0 plus C6 sine 0. Cosine 0 is 1. Sine 0 is 0. So this equals to C5. And this has to be 0. Okay, this has to be 0 because X0 is 0. Okay, so now we have C5 0. So our only hope is C6 not being 0. Okay, I feel like we are kind of repeating precisely the heat equation for this part. Okay, so now let's look at XL. Okay, C5 is already 0. So I'm going to write C6 now. C6 sine alpha L. Okay, C6 sine alpha L. And this has to be 0. So what should we do? Okay, so now we don't want C6 to be 0 because if C6 to be 0 is not a trivial solution. So that's why we want sine alpha L to be 0. Now alpha L has to be 1. Multiple of 5. Okay, you know, we don't want C6 to be 0. So sine alpha L to be 0. Okay, and then we have alpha L equals to n pi. Okay, it has to be equal to n pi. So that alpha, okay,
You can erase the bottom part.
Okay, I'm gonna erase. Okay, I'm gonna just then alpha. I just erase this part. Okay,
Oh. Yeah. Just not the bottom half.
I'll erase this part because I'll keep this part. I'll keep this two because I have done the ODE2, so I want to keep the ODE2 parts for
Gotcha,
you.
okay.
Okay.
If you could leave the bottom.
Okay.
Yeah, real fast.
So okay.
Yeah.
So then here you can see alpha equal to n pi over L. Okay, n pi over L, where n could be just any positive integers. Okay. So that we have here we get okay, I'm gonna just erase I'm gonna keep ODE2 there. I'll keep ODE2 here, okay? So that we have XX is going to be C6 sine alpha is n pi over Lx. Okay. C6, C5 is 0. C6 sine alpha x. Alpha is n pi over L. So this is my XX. Okay, so this is my XX. I'm gonna just put a square on this. This is my XX. Okay, this is my XX. So what about TT? Okay, that's like TT now. T. So this one. Okay, so let's look at this one here. This one here. Okay, ODE2. Let's look at ODE2. Finally, let's look at ODE2. ODE2. Okay, I'm going to use this. Okay, I'll just use this. We have ODE2 here, right?
Yeah.
ODE2 is this. ODE2. This is my ODE2. Okay, I just write here ODE2. This is ODE2. I just write it here. Okay. T prime minus a squared lambda t. This is my ODE2. Okay. So now because remember, okay, case 3 is this. Case 3. Now case 3 lambda equals to minus alpha squared. Okay, so this will become minus lambda minus alpha. So this will be a alpha square t equal to 0. Is that right? Yeah. Okay. So that pt, what is this? pt equals to what? Based on that same thing is third one.
Yeah.
It's the third one. Okay. It's gonna be, I already used C6. I'm gonna use C7. What is that? Cosine what? Wow.
Cosine or
A alpha.
A
Alpha. That is just my number 2. It's just the alpha there is A alpha here.
Yeah.
So it's gonna be cosine A alpha. What? T
C, yeah.
plus
C8 sine
A alpha T. Okay.
Yeah.
Of course, the alpha, we already determined alpha is n pi over L.
Yeah.
So it's going to write C7 cosine. Okay. It's going to be, I just write this n pi A over L T. Is that right? Plus C8 sine n pi A L T. Okay, so that's my TT. Okay, that's my TT. This is this. Is that clear? Okay, so we have an XX and TT. Okay, so let's look at the our solution. It's going. I'm going to erase. I'm going to erase here. I'm going to erase here. Okay. So thus you.
Oh, so we don't have to go through the 3 cases with ODE2 because we've already eliminated.
Yeah, because because ODE1 already eliminates case 1 and the case 2. Remember, ODE1 and ODE2 is actually the same,
Right,
it's the same thing.
yeah.
However, we have to utilize the boundary condition.
Right.
So that's why we started with ODE1.
Right.
ODE1 is about X, it's about boundary condition. So we started with their ODE1. Also, ODE1 is simpler. Okay, ODE1 is simpler, and also we can utilize the boundary condition to eliminate 2 cases.
Right.
So now we apply directly the third case to ODE2.
Okay.
Okay, to ODE2. Okay, because ODE1 is trivial solution, x equal to 0. So that's why it's x, then u is going to be x times tt is going to be
Right.
0 anyway. So that's
Right.
so that's why we so u is going to be xt is equal to xx times tt. Okay, based on here, it's going to be this times this. Okay, so it's going to be c6 sine n pi over L x times this whole thing. C7 cosine n pi a over L t plus C8 sine n pi a L t. Okay, great. Okay, so that's my. Okay, so I'm going to, apparently there's C6, C7, C8. There's 3 constants. I'm gonna just eliminate 2 of them. I'm not gonna eliminate one, just I call C6, C7 to be, say, A, and C6, C8, I call it B. Okay, so this will become, okay, I'm gonna just rewrite this as sine n pi L x. I call C6, C7, I call it A. Okay, I call it A cosine n pi A L t plus C6, C8, I call it B. Okay. Okay, and then I'm gonna do a little same trick we did before because it's a n. We can take different n's. So I'm gonna add a sub n here, and I add an n as the add a sub n. Okay. Because we can pick different n's in order to satisfy the initial condition. We haven't used the initial condition. We already so far we already used the this. This have been used earlier. This have been used to eliminate, the different cases. Okay, so we add a sub n. Remember, we are going to use principles of superposition. Principle of superposition means u can be written as a summation of all these UNs. In order to satisfy the initial condition, you can pick more than one n. We've done this before because fx and gx could be anything. So sometimes you might need to use unlimited, those UNs to represent fx and gx. That's what we did before. Okay. So let's look at the initial condition. Okay, let's look at initial condition. Initial condition. There are 2 initial conditions. Initial condition. Let's look at the first initial condition. Initial condition 1 is this. Is u x 0 equals to fx. Okay, u x 0 equal to fx. So what is u x 0? So now let's look at u x 0 is summation of all the un of x 0 when t equal to 0. Okay. Okay, so what is that? When t equal to 0, this is what? 1. Okay, so now we have, this is going to be summation of AN times cosine 0 plus BN sine 0. Okay, so it's actually AN
And
sine n pi x,
right.
sine n pi over L x. Because we plug in t equal to 0 into this.
Right.
Okay. So can you see that? Okay. Be able to see it, okay? So, okay, so this is, you can see this has equals to, okay, you can see n can be go from 1 to infinite, and go from 1 to infinite. This has to equal to what? Fx. Fx, yeah, this has to be equal to fx. Does this look familiar to you? Can we express fx as a summation of sines?
Yes.
We can. Okay, so this an will be the bn of the sine of the Fourier sine series. Okay, the Fourier sine series is
Kind of confusing.
I mean Fourier sine series. Let me see if I can open the Fourier sine series on the Okay, so I'm gonna just share this really quick for 1 second. Okay, so you can see here, this is the Fourier sine series, this portion. Okay, this is the Fourier sine series. Fx can always be written as a summation of sines, where Bn, this locate Bn equal to this. So we just have to make sure our capital AN equals to this Bn here. Okay, this Bn here. Okay, so and then okay, so that this is the Fourier right here. Okay. So my Fx is initial position. Okay, so if you have arbitrary Fx, initial position, I'm going to write down here, initial position from 0 to L is any function. I'll just initial position could be anything. Say, I'm just make some open like this. Okay, so this is my initial position. So this is my Fx. How to make this to be a sine? How to make this is my Fx. Suppose this is like a weird function to my Fx. How to make this to be a summation of sine? We have to do. This is only a half range from 0 to L. So what are the other half has to be?
Negative that essentially.
An odd reflection. So the other half has to be an odd reflection. Other half, let me try to make this to be like this, right?
Yeah.
An odd reflection. Okay, apparently this, so based on the Fourier sine series, this is an odd function can be written as a summation of sine. Okay, which is, you can consider this to be equal to what is the base one? Base one from minus L to L. That's the first one. I want to make this look like a sine. Okay. The base frequency is this, okay? Minus L. And then this is your B1 sine. What is the frequency? Pi over Lx. Why is pi over L? Because the period is 2L. So this actually has a omega. In this case, omega is pi over L. So that's why frequency is what? It's omega over 2 pi. So T is actually 2 pi over omega. You can see 2 pi over omega is 2L. T is 2L. T is 2L. So that's the base frequency. Okay. So that's why the base frequency has to be the period is from minus L to L. That's the first one. That's the first one. This is the base frequency. Okay, base frequency. And then plus 2 times of that. So this, you can see this equal, fx equal to this plus a b2 sine 2 pi over Lx. Okay. Then you can consider is 2. Okay, I'm going to just write 2. Okay, so I draw it this way. That means B2 is actually negative because it's right. So B2 is this. Okay, is this. B1 is the height. Okay, so this is 2 times. So this means the 2 times the frequency just appear 2 times as fast. Okay, and then you can consider this is plus and then keep plotting. Okay, now 3 times. Okay, 3 times. Let me make this to be. I'll make it 3. Is that 3? 3 cycle 1, 2, 3. Is that 3 cycles? No. 1 cycle, 2 cycle. No, that's not 3 cycle. I need to make it precisely 3 cycle. So, sorry, I'm a little bit sometimes. Okay, that's 3 cycles. Okay, that's 3 cycles. Okay, that's 3 cycles. So you can plot a B3 sine 3 pi over Lx. Then you can keep going. This can keep going. Okay, so that's why my AN has to be the coefficient here. AN has to be the B's. Okay, so that's why for this case, AN has to be equal to BN for Fourier cosine series, a Fourier sine series, which is that in that. Right. I'm sorry, I should stop sharing. Okay, so I stopped sharing because if I don't stop sharing, the recording will see a little small portion of the board. Okay. So I stopped recording. So AN has to BN of the Fourier sine series. We just copy there is what? 2 over P. P is L. Okay, is 2 over L.
Over 0 to L.
So basically, I'm going to write Fourier. So Fourier series is okay. Fx equals to n from 1 to infinite. Bn sine n pi over Lx. So in this case, you can compare this with this. So our AN has to be the Bn. So that's why our AN has to be equal to the Bn of Fourier sine series, which is 2 over L, 0 to L, Fx sine n pi over Lx dx. Okay. All right, so this, and then what else? What should we do next? So now we determined the AN here. We have determined Bn. We need to determine Bn. Okay, now we need to determine the Bn. How to determine Bn? Okay, I'm going to use their board. I'm going to erase. Okay, how do we determine Bn? So we already use this one. We have one condition. We have one condition we haven't used. And we have one coefficient we haven't determined. We have this condition we haven't used.
Right.
We have this one, Bn, we haven't used. Okay, so what is the okay, so let's look at how to determine. So apparently we need to do this one. Okay, so I'm gonna just use the other side of the board. I'm gonna move the board a little bit. Okay, what is our solution, by the way? Our solution is this, okay? Let me just write our solution again. Our solution is U x t equals to this thing here, okay? This thing here, all right? This summation of this, okay? It's the summation of sine n pi Lx. I'm just rewrite this, okay? This and this together is going to be an cosine n pi over n pi a over L t plus bn sine n pi a L t. That's actually our solution. Okay, now we determine an. Okay, we determine an is this. An is this. We need to determine bn. And then we have one more initial condition. Okay, now let's look at initial condition 2. Initial condition 2, which is what? Partial u, partial t, g equals to 0 equals to gx. Okay, now let's do partial u, partial t for this one. What is partial u, partial t? Right, partial u, partial t. If we do partial u, partial t, this one is considered what? A constant. Okay, so we do this a constant. So this constant, you can still write it there, n pi over Lx. What about the derivative of this in terms of t?
Negative an sine. Oh, God.
This thing you can take it out, right?
Yeah, multiplied by that.
It's
So,
just n pi a L sine.
sine.
Okay, n pi a L t plus bn.
Bn.
Same thing.
N pi
N
a.
pi a L times
Cosine.
cosine n pi a L t. Okay, so that's the. Okay, so that is your. That's the. And now we have we have to t equals 0.
Zero, right?
Initial velocity. Okay, plug in t equals 0. This will be sine 0 will be what? 0 and cosine 0. Okay, so this will be. This will becomes n from 1 to infinite.
Bn.
Bn. This okay, will be Bn n pi a L times 1 times sine n pi over L x. Okay, this has to be equal to gx. So, okay, so what is this now? This is also a Fourier sine series.
Yeah.
So this is also a Fourier sine series. Okay, so basically it's like, gx apparently based on Fourier series, gx can be write as n from 1 to infinite or bn. It's a different bn from that one. Okay, sine n pi over Lx. So this bn has to be this entire thing. This entire thing has to be bn, where bn is based on gx, not fx anymore. Okay, where bn, so basically you can say bn, where bn is going to be 2 over L, 0 to L, gx, not fx, gx sine n pi over Lx dx. So this entire thing is still valid. It's just the difference is instead of fx, it's just a gx. For example, it's a gx. I don't know what the initial velocity of gx. Gx could be something different. Let me say, okay, I'll just make it. Suppose gx is like this. I'll just make it something. Okay, suppose gx is like, okay, it's like this. Suppose it's like this. Okay, I mean, it's arbitrary, so I just make it like this.
Yeah.
Okay, I'm just saying it's supposed to be linear. I mean, it doesn't have to be linear. It could be anything. Okay, it could be anything. It cannot be anything because the two ends are fixed. So the ends cannot have a velocity. Okay, so it has to be supposed to be something like this. Okay, something like that. Okay, because two ends are fixed. Ends cannot have a
And
velocity.
it must be linear because the derivative is 0.
What's that?
No. Never mind. Take it back. Keep going.
The two ends has to be fixed. So
Yeah.
two ends cannot have a velocity.
Right.
Okay, so I'm just draw this. This actually is arbitrary. I just say it's supposed to be like this. Okay. Okay, so what is my Bn? So my capital Bn will be what? This has to be equal. This has to be equal to this. So capital
Right.
EN will be EN times reverse of that. L over M pi A, which is this times this. L and actually canceled out. Is 1 over M pi A, 0 to L, GX, sine
Would it be 2 over?
M pi L X dx.
It'd be 2 over.
That's 2, okay. That's 2. Okay, 2. So this is my BN. So my final solution is whatever I put into the square. Okay, is this where AN is this, BN is this. Okay, so that's my final solution. So the final solution, I'm going to write the final solution. I'm going to write the final solution together.
Where you can see it.
The final solution, I just write it here. Okay, solution is this in here is U X T equals to summation of n from 1 to infinite. I'll put this in front of this, doesn't matter, okay. I say AN cosine M pi A L T plus BN sine M pi A L T times put the X behind. It doesn't matter with T, okay, sine M pi over L X. That's that, right?
Yeah.
I just swap that, doesn't matter because the book swap has division.
And
Where AN equals to this is 2 over L, 0 to L.
Yeah.
At the X sine M pi over L X dx, and BN equals to 2 over M pi A 0 L GS sine M pi over L X dx. So the whole time I just get, this is the problem, this is the solution.
so
Okay.
would you accept that as a solution? We don't actually have to write in the AN into the Fourier series?
What's that?
Would you accept that written as it is as a solution?
Yeah, there's no way to simplify further, right?
Well, no, I mean, you could write it all as one
Or
long.
you could write it as all one, yes.
Yeah.
You could put this, plug this into this, plug
Right.
this into this.
Yeah.
I somehow prefer to
Me
separate
too.
them.
Yeah.
Okay, you could write a long equation, just there's no A and B and, you just plug this into this, plug this into that. That's one single solution. Okay. So I'm done this. I'm gonna run the simulation. So I'll take if you have time, that's awesome. Okay. So that's awesome. I'll take like a 5 minutes break and then we're gonna run the simulation. So I'm gonna stop recording for a moment. Pause. Okay, so let's run a MATLAB simulation. So MATLAB simulation is going to be this problem here. Let's see, it's based on our book. .13.4. Problem 7. Okay, problem 7 of the exercise problem 7. That's from the I'm gonna erase all this. So let's run a MATLAB simulation. MATLAB simulation for exercise number 7. Okay, exercise number 7 is the initial condition. So let's make this to be, we call this to be a plot string. What is a plot string? Plot string is a special condition of this is when gx equals to 0. Okay, when gx equals to 0. That means initial velocity is 0. Okay, so that problem is, that means the string is released. The string is released from rest. The string, that it also means the string is released from rest. Release from rest means velocity, initial velocity is 0. Okay, its initial velocity is 0. So the string initially is this one. Okay, let's say initially the string is, think about you have your hand. You use your hand to pick up the string. You use your hand to pick up your string in the middle. Okay, this is L, this is 2L. You pick up the string in the middle, and then you raise it to the height of 1. Okay, you raise to a height of 1, and then you release it. You raise to a height of 1. Okay, you raise to a height of 1. This is 1 here, and then this is 1. That means you think about your hand pick up. You not just pick up, you hold it. And at t equals 0, you release it. Okay, so that now will make a plot string because when you hold it, that means it already has a velocity of initial velocity of 0. So means then you release it. Okay, so then you release it. So let's suppose L, to make it simpler, let's suppose L equal to pi. Okay, for simulation purpose, let's suppose L equal to pi and A equal to 1. Okay, just so it's simpler. Okay, now L is pi, A is 1. Okay, so let's look at then what is our, okay, so now our solution is what? Our solution is, in this case, solution is becomes, okay, let's see here. U x t equals to n from 1 to infinite, an cosine n pi, a is 1, L is pi, so it's nt cosine nt plus bn sine nt times sine nx, right? Becomes sine nx, where an is this, bn is what? bn is 0 because gx is 0.
Yeah.
Okay, so where an, so it's actually bn, you can see that bn is 0 because the gn is 0, because gx is 0, so bn is actually 0. Okay, so from here you can see a n is going to be 2 over L, 2 over pi, 0 to pi, fx, sine nx dx, bn is 0. Okay, so that we have u xt is actually quite simple. n from 1 to infinite, an cosine nt sine nx, okay? Where an is this, okay? Where an is this. Okay, well, I'm just plug this in, okay? Well, let me see this, okay, this is this, okay? Where an is. Okay, so that's the where an. So I'm going to write it here, okay? I'm going to write it here. Our u xt is going to be a summation of n from 1 to infinite, an cosine nt sine nx, where an is going to be 2 over pi 0 to pi fx sine nx dx. Okay, what is fx? I wanted to write what is fx. Okay, what is fx? So this is the end. Is this okay? What is fx?
Do we have an answer for that?
No, this is.
Yeah.
What is this fx? How do you write this fx?
Oh,
What is function of fx? This is my fx.
these ones would be,
This is my fx. Okay. Of course, the initial position.
yeah.
Right? Initial position.
that would be, from where x from 0 to pi over 2, is equal to, oh god, what would the slope be?
What's the slope of the half? This is pi over 2. Okay.
Yeah.
What's the slope of this first half? Is 1 over pi over 2.
Pi over 2, yeah.
So 2 over pi.
2 over pi, yeah.
Okay. So it's so the left half is 2 over pi x, right? Because that's the slope of this.
Yeah.
Which is this point, because this point is x equal to pi over 2. Think about this point is pi over 2 1. This point is pi over 2 1. X equal to pi over 2,
Right.
y equal to 1. Okay. So what about this half? This one here,
Negative.
slope. It's negative of this. What is that? Plus c. Well, what's plus c? What? Plus 1.
Plus 1, yeah.
Plus 1?
Yeah.
Plus 1? How did you get 1?
Because it's from 1. No, it'd be plus, yeah, you're right.
When x equal to 0, you think
Yeah.
about this extension of this. When x equal to 0, the cross section,
Right.
when x equal to 0, this will be 2, so plus 2, okay?
Right.
Plus 2, okay? Okay, so this is this. Okay, you see that? Okay.
Yes.
I'm going to erase this. Okay, that is my solution. Okay, and this is where this is for x go from 0 to 1. This is from
0 to pi.
0 to pi over 2. This is pi over 2. Okay. Pi over 2 to pi. So this is actually our solution. So this is the solution because of this orders L equal to pi, A equal to 1, and fx, gf equal to 0. So this reduced into this. Okay, our fx is specific to this particular initial position. Okay, so we're going to run simulation just for this right now. Okay, for this. Okay, for this. So let's run the MATLAB simulation. Okay, I'm gonna share screen so I can open MATLAB. Okay, so I'm gonna open a new one. Oh, why open two of them? Okay. Can you see it clear on this? Do I have to magnify this? Okay, okay, that is fine. Can you see it? It's gonna be a little small, okay. So I'm going to do symbolic calculation to evaluate this. Yeah. Okay, I use because I can do it by hand. Can you do it by hand? Of course. You can do it by hand. It's just x sine and x. Here it's also x sine and x.
Right.
You use integration by part. It takes a little bit of time, but you can actually do it by hand. But I just let MATLAB to do it for me. Okay, so I'm going to do it here. I do want to change the resolution so that you want me to change resolution for
Fine.
on with it?
Yeah, I mean, if you're comfortable, right?
Okay, I think I will just keep this like this. Okay, so I'll do symbols. Sims in here, x and n are two symbols. Okay, sims and x n. It is a little small, but I think I'm gonna still change resolution. Okay, I just make it a little. Okay, sims x and n, and then I have integration. Okay, so integration, you see this fx is this portion and this portion. So you basically, essentially, you're doing integration from 0 to pi over 2 over this, and pi over 2 to pi over this function. So I call f1 and I call this to be f1. I'll call this to be like f1 and this to be f2. Okay, so just then I call f1 equals to 2 over pi, 2x over pi, okay? 2 times x over pi, okay? And, okay, good. F2 equals to, I do call it minus 2 times x over pi plus 2. Okay, is that right? 2 plus 2. Is that right? I think so. I think that's right.
Yeah. I mean, if you want to put the first term in.
Okay. And then I have an equals to, I do integration of f1 times sine and x. Okay, f1 times sine and x. Okay. I just make sine and x to be f1 in part of f1 and f2, okay? So that I just do f1, okay?
Okay.
Is that okay? So, okay, I just put it here.
Yeah, times sine and
Put it times up. Times sine and x. Oh, you cannot change it. Okay,
No.
I already. It's fine. Okay, you cannot change it because it is already. So sorry. Okay, let's do this. X go from 0 to pi over 2. Okay, pi over 2. Is it right? And then plus, I just copy this integral. This is f2, right? F2, and then instead of pi over 2 to pi. Is that right? I think so. And then don't forget the 2 over pi, okay? The 2 over pi here, okay? So times 2 over pi. Is that right? Times. Okay. Can you see that? Okay. So is this times sine and x? Okay, I wanted to put there. Okay, this is f1 times sine and x in terms of x goes from 0 to pi over 2. And the integration of f2 times sine x in terms of x goes from pi over 2 to pi. Okay? Okay, now I have a an. So I just copy this an. Okay, I copy this an to my equation, to my script. Okay, that's my an. I copy the entire thing here. This is my an equals to this. Okay. Did you get it?
I think so. Wow.
Let me check yours. Okay. Let me check yours really quick. Oh, you're doing, did you get, okay.
Yeah, doing full, sorry. Yeah.
Why yours is F1? Where's your F1 and F2?
Right.
Okay. Oh, okay. You should have an parenthesis here. Okay, that's why you have issue.
Oh, yeah, no.
So now you
fix it here.
That's why. And then that's you to pi. Oh no, this should be.
Oh, okay, so
This should be, yeah, that's still not right.
Okay.
Because I have to do this. Okay, so this pi over 2, so this should be parentheses. Oh. One. This. Well, integral pi over 2 sine x.
There's too many parentheses.
Yeah, this.
Yeah.
And that's just pi.
Yeah, there we go. Okay.
Okay. So that's my an. I copied it here. So I'll do the programming now. Here all. Right. And this is actually very clear all. Okay, clear all. And then I do. Oh, why is this change? Okay, sorry, I moved it. Okay, now finish this. X goes from 0 to pi with increment of 0.01 to pi. Okay, so that's that. And then this is what I'm going to do here. Okay, I'm going to do the let me see. I'm gonna do a for loop for this. So in this problem, I'm going to run the cartoon. Okay, I'm going to run the cartoon. What? Let me see. Your might be there. Let me see.
See, cosine, this is the cosine pi.
Okay. Yeah, sometimes depends on their order you put, it might look different, but the answer should be the same, like integral f1 times sine and x. Oh no, you forgot this. You forgot this.
Oh, that makes sense.
You can do it.
Yeah,
You can do it in the code. Okay. You forgot times 2 over pi. I did add it at the end. Okay. I did add it at the end. So just you have to add that. Okay. So I'm going to do, this is what I'm going to do, okay? I'm going to do the, for time, I'm going to plot this at different fixed time. I'm going to plot this at fixed time, okay? And then if I loop it, then I can see a movie, okay? So I'm going to do this for T, I don't know how long I'm gonna run, go from 0 with 0.01 as increment to say 5 seconds. Okay, 5 seconds. I loop it. So I plot it every time, at every time point, I plot the position. So if my frame, if I have a little small time step, then my eyes can see like how the string will vibrate. We can see there kind of like a movie how the string vibrates. So for T, go from 0 to say 5 seconds with increment of 0. Okay, I'm going to say 4, then I'm going to do 4 and go from 1 to 100. Let's do 50. 50 should be good enough. And then AN. And then position U, start with 0, for example. And AN is this. What is the B? And then I'm going to do the, oh, so long. Okay. And then I'm going to do what? I'm going to do this. Summation is a for loop, AN cosine NX. And I say U equals to U plus, okay? Do you remember this? U equals to U plus AN times cosine and T times sine and X. Is that right? Okay, and then what should I do? Can you see that? Okay. For every I do a for
yeah, you need a.
for T, I do a for loop. So I do the plotting at every time. At every time I plot it. I think about this. If this is T equals to 0, T equals to 0 is this. Then T equals 0.1, 0.01 I plot it. And T equals 0.02, T equals 0.03, T equals 0.04. And I plot it. And then you can see it moves. Okay, then you can see it moves. If I keep overriding previous plot, then you can see it moves. So I'm gonna do plot X against U. Then I will add a little bit pause. I normally say draw now, and then pause for a little bit. Pause. I don't know how long should I pause, say 0.01, for example, second, and end. Okay. Are you comfortable with this?
Just, there we go.
So I'm gonna plot it now, okay? I'm gonna plot it. Wave equation, I call wave equation. Where's my plot? I think I have a problem here. Oh, cosine. I spelled it wrong. Cosine. Okay. Okay. Now, can you see the movie? It moves. What is the problem here? The y-axis is not fixed, right? Because it is actually a movie because the range actually keep moving. So it does not really make a lot of sense. So I'm gonna fix the range. Okay, I'm gonna fix the range. So I'll fix the range. I'll fix y, especially y, because y limb. So I'll fix it from because it should vibrate from 1 to -1, right? I can just do 1 to -1 to 1, or I just add a little bit, maybe -1.1 to 1, -1.1 to 1. Okay. So this is sort of like fix the range. Okay, the fixed range, so it's not keep moving. Let's do the plot. You see it? Does it make sense, the vibration?
Yes.
It kind of makes sense, right? Okay, so I'm gonna fix the x-axis too. I'm gonna fix axis from 0 to pi. Okay, I'm gonna fix axis from 0 to pi. So I do this. Axis, I go from say 0 to pi, 0 to pi. Okay, and I'm gonna make this line to be a little thicker. So this can call the line width. I'll make its thickness to be a 2, for example. Okay, so this will make the line a little thicker. Let me just plot this. Oh, where is it? Sorry, I didn't. Okay. Oh, how come their x is not fixed? Okay. All right. Okay. Oh, x limit from 0 to pi. Do it again. Okay. From minus 1.1 to 1. Okay, let me see. From minus 1.1 to 1.1. I'm sorry, to 1.1. So it's symmetrical. And this is the vibration. So I fixed y from minus 1.1 to 1.1, x from 0 to pi. So that is kind of it's always part of the same range.
What's going down in your
My code. So you have to pause a little bit. Otherwise, the program runs too fast. Your eyes wouldn't be able to catch the vibration. Okay. So for this problem, it's a little different from the heat problem. For heat problem, I plot in the two-dimensional surface, right? In this case, I didn't plot two-dimensional surface. I just plot the I plot u at fixed time. Okay, u as a function of position at fixed time. At time equal to 0, time equal to 0.01, time equal to 0.02. I just override previous plot. If I override previous plot, then you can see a movie. Okay, so that's why here you can see what is the size of u. Size of u is the same as size of x in this case. You can see here, size of u is the same as size of x, so that you can plot x against u. Because because in heat equation, I plot a 2D surface, but here I can also plot a 2D surface if you want, just like the heat equation. But I feel like I want to see the vibration, so I just, instead of plot a 2D surface, I just plot u as a function of x at different time, at fixed times. Okay, if I plotted them continuously, keep overriding previous ones, then you can see a movie, how the string vibrate. Okay, so if I want to know what is position of, for example, if I want to know what is the position of string at time equal to say 100 seconds, how did you do? I just changed this. Look at the code here. If I want to know what's the string, I just change this to. I don't have to do that. I don't even have to do this. I just say 100. Right. Okay, let's see what's the string. And then you will have a position. Okay, this is what happened when p equal to 100. So you don't plot the whole time from 0 to 100. You just plot p equal to 100. Okay, I just change this to be like a t equal to 100.
Can you go down again?
Okay, in this case, I don't even need a for loop. You want to plot 6 times. I don't need a for loop because you are not looping it, okay? So let's do this again from 0 to. What do you want me to show you?
Your line, I think it's 13.
That's how you vibrate. Oh. Okay, I'll show you the code. What code?
YLAM. Oh, you need brackets.
Okay. Yeah, it means I plot X from 0 to pi. That's the range. Y then I go from -1. You can go from -1 to 1, but I always leave a little bit clearance. So, right. Okay. So hopefully you can get an idea. So even the solution of the wave equation looks super long, but if I use a specific example, when I plot it in MATLAB, it makes sense. It makes intuitive sense. The string should vibrate like, because if this is the ideal case, there's no friction of air friction, anything that, so they would vibrate forever. They would vibrate forever between -1 and 1.
And that's because A equals 1.
Okay. A is, I don't think the A, no, if A is not 1, I don't think it change. It's more of it affect I think it's there. You know, when T equal to 100 may not be look like in that position.
Yeah,
I don't think it changed the range because this is ideal. Suppose the string
Right.
is vibrating in outer space. There's no gravity, there's no air friction or anything, air resistance. It just vibrates forever.
Yeah, but
Okay. I think A affects the. I'm not a mechanical engineer. A probably affect the. Like they would at different time they would have in a different position.
Right.
Okay, I think they affect how fast they move or something like that, but it wouldn't affect the range. They will always go from -1 to 1.
Yes.
Okay,
Yeah.
they will all go from -1 to 1 because this is perfect elastic string
I thought that
without gravity and without resistance from air. Okay. Okay, so I think I'm gonna stop sharing, so I'm done today.
Oh, we're good.
Okay. All right, I'm done today. Okay. I think hopefully Melissa's still there, but I'm gonna save their recording. I'm gonna share it with the class on Canvas.
Thank you. Have a good night.
You too. Bye.
Bye.